We are also in YouTube.
Okay.
So it is a time. I think we can start, yes? Let me just introduce you and for you about ourselves. So
Sure.
we are from Uzbekistan, and we have 6 Uzbek partner universities and also non-academic partners. And my name is Habibullah Nasirov. I'm a head of a department, but from yesterday I'm a dean of one faculty. And this project is very big project for us because it is first time in Uzbekistan. We are like a grant holder in Erasmus project, and this is first time in Uzbekistan, and this responsibility for our Uzbek partners and also for our university. And it's great pleasure to see you in a good mood, in healthy this kind of very difficult period of time with this kind of pandemic. And as you know, your vice rector and vice president of European Affairs also give a speech in our opening ceremony. And if you are ready, I can just say that we have our professor from Sorbonne University, Paris, France, Julien Sarrazin, with his topic of today's work, like antenna design for 5G communications. And floor is yours, please.
Okay, thank you very much for the introduction. Hello, everyone. So my name is Julien Sarrazin, indeed, and today I'm going to present the course I have shared about advanced antenna and propagation concepts for 5G. So I will start by introducing myself and a little bit of my research before getting to the course. And please feel free to interrupt me. I know this is online. This is not easy for interaction, but I have put on my screen the chat, and I also can see if you turn on your webcam. So if you want to interrupt me, you can do it in the chat, or you can just talk. I mean, please feel free to interrupt and to ask any questions, whether it's context or technical or whatever. Please, really feel free to interrupt me. So I'm sorry, I'm not looking at the camera because the camera on the side, my screen is on the other side. So I myself belong to Sorbonne University. Yes, to Sorbonne University. Sorbonne University is actually several universities that have merged, and now the organization is as such. We have a faculty of science and engineering, one of medical science, and one of humanities. So naturally I belong to the science faculty, and within which you have several departments: biology, chemistry, earth, environment, and biodiversity, engineering, to which I belong, mathematics, and physics. Within engineering, you have 3 sub-departments. One is about computer sciences, electrical engineering, and mechanical engineering. So I belong to electrical engineering. So physically, I am based on the main campus of the science faculty, which is right here. The name of the campus is Pierre and Marie Curie campus. Pierre and Marie Curie is actually the old name of our university, the science part. And so it's located in the center of Paris. For those who might know, this is the Notre Dame Cathedral, this is La Bastille, and this is the Panthéon. So it's right in the heart of Paris. It's a nice location. And this is the campus. This is the main campus of the science faculty of Sorbonne University. So you see, it's a campus dedicated to science, and there are, even the architecture is very much scientist. It makes a lattice, okay, a rectangular lattice, the buildings. And if you come to visit us, it's very easy to get lost within these buildings. But there is a trick. You see, that is sorry. I lost my, yeah, as I mentioned, that makes a rectangular lattice, and it's like a matrix for who are used to work with matrix. So you have columns, you have rows, and the intersection between buildings actually has the name, has the number, and the first index is the column, the second index is the rows. So you see, this will be the diagonal of the matrix: 6, 6, 5, 5, 4, 4, 3, 3, 2, 2. And as you can observe, there is no 1, 1. They started the construction, and by the time they reached the first column, the plot of lands was taken away from the university. Of course, you're in the center of Paris, so each square meter is very I mean, people want land there. So here instead, it's a museum. It's a very nice museum, and you can actually go freely to the rooftop, and you have a very nice sight of Paris. So this is a closer look to the university campus. Those are the lattice I was talking about, the matrix, and in the center you have this tower. This tower is where you have the administrative services, like human resources or president of the university, vice president, etc. The researcher, so from that building, you have a very nice sight of Paris. If you come to visit us, I highly recommend you to ask anybody to bring you to that top floor. It's probably the best you can have in Paris. And the buildings around are where we researchers and professors are, as well as the students. So we don't get to have the nice view. So all those buildings are either classrooms or research facilities. So I belong to Sorbonne University, which is my employer, but in France the system is a little bit complicated, maybe unnecessarily. You belong to a university, and at the same time you belong to a research laboratory or a research institute. We have both, and my research institute is called GIPS. It's the Group of Electrical Engineering of Paris. So it's a research institute, and to even further complicate the story, a research institute can belong to multiple universities. So it's the case with mine. The GIPS belongs to Sorbonne University, as well as Université Paris-Saclay, which is another very large university in the south of Paris, to Centrale Supélec, which is, it's something a bit typical to France or Germany. They have the same. It's an engineering school, so it's pretty much like a university at a smaller scale. And in addition to that, we also belong to the CNRS, which is the French Research Committee. So it's not a teaching entity, they do only research. So within my lab, you can have people, professor from Paris-Saclay University, from Sorbonne University, from Centrale Supélec, and you can also have researcher from CNRS, who are most of the time not teaching, just doing research. So with the GIPS, this laboratory is composed of 3 departments: electronics, energy, and material, all dealing about electrical engineering. So that goes from power electronics like electric cars and all, to energy with solar cells, for instance, to electronics with devices, and also electromagnetics, which is quite a large component of our laboratory. We do a lot of numerical methods, numerical modeling of electromagnetics, either for low frequency or high frequency. So this group is about 250 people working in those fields, and within the I'm a member of the electronics department, within which I'm the coordinator of a team of about 20 professor and associate professor, and we work in wave and propagation. So I will first give you some hints about the research we do within that team. Before I actually come to the core of the presentation about the course. So in our team, we work in, we study electromagnetic wave propagation mainly, either to understand some physical phenomena or to design some new systems for multiple applications. So just to give you examples, we do a lot of modeling. So in complex environments, complex can mean very large problems, or it can mean very large or very complex in the sense you have a lot of different criteria to take into account to do those kind of modeling. Just to give you an example, we do a lot of human body modeling. So we investigate how electromagnetic wave does propagate through human tissue. And we also build phantom that mimic the electrical properties of human people with respect to those electromagnetic waves. So behind this, we want to assess it's for medical engineering mostly. We assess the medical imaging technique or medical hyperthermy, where you transmit electromagnetic wave to kill some cancer cells. So this is one of the applications we are working on. We also do complex environments, such as this is a reverberant chamber. So this is like a Faraday cage, a metallic room, within which you can control the propagation of electromagnetic waves quite accurately and statistically. This is a powerful tool to test some devices, their robustness to radiation, or simply to test some communication device to mimic some propagation environments. And we do also a lot of electromagnetics designs. So we do a lot of metasurfaces, which are engineering, like metamaterial. We engineer material. We do so either to control guided waves, so to produce devices such as, so this is an example of a planar lens, but it could be filters, phase shifters, so electronics components for high frequency. And we also control radiated waves to make antennas. So this is an example of a leaky wave antenna that leaks through a holographic impedance surface. So specific antennas for dedicated application. So the applications lie in so medical, telecommunications, radar, space application, but most of the time what we end up doing is either to detect or localize some objects, or focus some power or some data towards some area. So some examples, as I mentioned, we do a lot of antennas. So, but it's broader than that. We have tools to generate any radiation we want, and from that, we using some technologies, we build devices. So this is an example of a reflector that operates at the terahertz frequency. This is to split up the beam of a local oscillator. So this is a device that is for satellite, for imaging, space imaging. So observation of the space, basically, at terahertz frequency. We do also health application. This is a project of indoor localization and heartbeat detection. So it's a wireless heartbeat detection to detect some emergency situation using electromagnetic waves at 60 gigahertz. Other applications, here we are in the HF, so it's much lower frequency, it's at 10 megahertz approx. And this is beyond the horizon radar. So you have radar nearby the sea, and each government needs to check the boats that are within his zone area. And you have either line of sight radar that doesn't go very far away to observe the boats because of the curvature of the Earth. You have also an operation where you send a wave that reflects on the ionosphere and goes behind the horizon, but you go much further. But in between, there is an area just behind the horizon that is not easy to detect from the coast. And we are developing new types of radar where we use surface wave excitations so that the wave will be guided along the curvature of the sea, and you can actually, the radar can see beyond your horizon, just beyond that. And we do also, this is a telecommunication application, it's geocaching, it's multiple antenna-based recording, something I'm going to talk for this course, where you want to send data only to specific areas. So it's known as geocaching. You broadcast data that can be decodable at some specific area only. So this is a mix of signal processing, propagation, and antennas. Just to conclude on that, I will give a few words on my personal current research. So my background lies in antenna design. So I'm from mostly electromagnetics background, but I've worked also on multiple antenna techniques. So I have come close to signal processing and digital communications. And now I would say I'm in between, I'm at the interface. So I still have, so I have two main areas. One is in electromagnetics, the other one is in signal processing, we could say. So I do antenna and electromagnetic device design. I do localization techniques, taking into account the propagation channel. And I work quite a lot at 60 gigahertz. And I do physical layer security and spatial data focusing. Those are signal processing techniques, the recording. So it is closer to digital communication. Physical layer security is when you want to make a wireless communication secure without necessarily needing a key. So it's not based on cryptography, it's based on you pre-code the data, and anywhere else but at the legitimate user location, you cannot recover the data. The data scrambles. So this is an area of research right now for me. So that's about the background of a group and myself. And knowing that, I will present now the course, Advanced Antenna and Propagation Concepts for 5G, so fifth generation of mobile communication. Some keywords, 5G, MIMO systems, I'll be explaining MIMO systems, multipath propagation, diversity antenna, millimeter wave arrays, digital communications. So for those who are in this field, these keywords, of course, ring a bell, but I will try to give a brief overview of what those keywords are and why it is important to understand this if you work in telecommunications nowadays, especially if you are close to the radio access network, close to the antenna side. So the syllabus of the course is divided into 3 units. The first one is a general introduction to 5G and some background. One is the focus on the MIMO technology and its influence on antenna design. So it mixes signal processing and antenna. And the third unit is also MIMO, but for millimeter wave, which has specific issues. So the approaches are slightly different. So this course is pretty new. I have done it for last year, and I have taught it twice actually, before two different publics. One was beginning of last year in IIT Bombay, so in India, university in India, and once was as part of unit at Sorbonne University in our master degree. So I will just give a brief overview of these two experiences before explaining the course. So the first time I've built the course was for IIT Bombay. Actually, I was invited as a professor, invited professor there in July 2020. It was an elective course. There it means elective course it's an option that student can take, and they can take no matter what, no matter their background approximately. So within the class there was people from bachelor degree, under master degrees, or under PhD degree program as well. So it's very tricky because you have different programs, different backgrounds from students. Some students were from digital communication world and wanted to know more about 5G. Some people were more about antenna design and they wanted to know more about the signal processing. So it was a mix of people. And I will talk about that later on, but there is always an issue of prerequisites when you develop advanced classes, because as you will see later on, this course needs quite a lot of different backgrounds in different fields. So it's not easy for students to have all the backgrounds. So every time I've done this course twice to two different classes, and every time I had to reconstruct the first unit to see to reintroduce some backgrounds and some prerequisites depending on the students. So to give you an idea, just the general introduction was about half a month. The second unit was the largest one, so 2 months, and the third unit about millimeter wave was 1.5 months. So it was a 4-month course, and you had no practical but projects. So on top of that, approximately at the mid-semester, we started some projects, and I was giving some. It was very open. The students could choose whether they wanted to do more signal processing based projects or electromagnetics projects. It was really depending on their interest. So the course there was about 3 hours per week, either three times 1 hour or twice 1.5 hours. And if you want to have a look, they actually did record the classes as I was giving, so you can check on this link. I will make the slides available. I think if you click on it, you have to register, but it's free registration. You basically just give your email, I guess, and you can see the video of the course. Unfortunately, only the 2 first units video are available because, as you know, half the semester the COVID situation rise, and so we couldn't video record the end of the semester, the second half of the semester, actually. So, as I mentioned, I gave this course also this semester, which is about to end. In France, the first semester starts in September and ends usually in January. So I'm giving this course for our master students for the last year of the master. And this course is part of a slightly larger course about wireless communication. So at Sorbonne, we have a master in engineering, within which you have the master in electrical engineering, within which you have 3 specialties. One is about sensors and measurements techniques. So it's a mix of physics and electronics, basically. One is health engineering. So it's electronics, a bit of mechanical, and quite a lot of medical background. So it's really a mix between engineering and medical science. So the students there, they have classical engineering courses, but they have also courses at the hospital. So within Sorbonne, we have hospitals, and they go to the hospital campus to have courses, lectures by the surgeon or whatever the specialty they have taken. So usually those classes, because they are given by medical people, it's late in the evening because the surgeon do surgery during the day, and they will teach classes during the evening time, like after 6. And the third specialty is the one within which I'm involved. It's communication system. So it's a master degree. I'm going to present this master degree to give you an overview of what is the background of our students when I'm giving this course. Just to mention, this master can be followed as a classical courses, so just a normal classical one, or as apprenticeship. So that is, the students, they will have 3 days on campus following the classes and 2 days working in company. The thing is that they are mixed with the classical courses, and actually it's a very demanding courses because they have approximately the same amount of teaching of classes, except for maybe a couple of courses. They have to follow everything to give the same exam, to be the same classes, and they have on top of that 2 days in companies. So it's good because that gives them an experience in companies before even the end of their master degree. That also, it's good financial support because they are paid by the company, but it's very demanding because it's a complete master degree and you work on top of that. So it's we do quite a strict selection on the students because not everybody can follow these courses.
Sorry, may I ask?
Yes.
So that is not like an internship, yes?
No, the classical courses students, they will for internship. The apprenticeship,
I mean, it's the last apprentice.
Yeah. This is not like internship. It's like every week they're working in the company, and they have, when the other students, they do internship, they just work full time in their company, the other ones. So it's different, and they have a proper contract. So yes, they're really engineer in a company actually, but just part time, 2 days a week.
And again, I mean, the master students will get the money from company, yes?
Yes,
not
that's right.
Paying for company engineers for teaching them.
No, it's the company that pay for the students' money, and I believe the company does also pay our university.
Whoa.
Yes, I think so. I think so. I'm not quite sure. I think so. It works like this. They give some support. Yeah. Yes.
And how many? Sorry. How many students can be involved in one company, or it depends from the company?
Yes, in our master degree, in this specialty, there are about 25 people, among which 8 are doing this specific apprenticeship, and the 8 are in 8 different companies. But it's up to them to find the company. So at the beginning of the year, what happens is that some students have found companies, some other not, and we give them till December to find the company. Otherwise, they just shift to the classical courses. We help them, of course, but
so this is also not mandatory, yes?
There is a way out. I mean, if you didn't find the company, you will just go back to the classical courses. Yeah, because they're basically following the same classes. So
okay.
All the classes, they are in the 3 first days of the weeks, approximately.
Okay. Thank you. So it is in the master, not bachelor.
Exactly, it's in the master. In the bachelor, I'm not sure in the bachelor. There might be also some similar stuff for the last year of the bachelor. I'm not very aware of it.
Because for us, we have in bachelor 3 types of internships.
Okay.
Like in a second year, our bachelor is 4 years. In a second year, students will be in a university, so understanding which direction they are learning. In the third year, they have internship, like a full time, and
Okay.
in the fourth year, they are making internship in a companies
Okay.
similar to this what you told, but it is also involved full months, like 2 months they have internship.
Okay. Okay.
But
Okay.
this is also very interesting. Thank you. Sorry.
Thank you. So yes, they basically follow the same classes, and so the skills they are supposed to acquire during this master degree are related to radio frequency and microwave systems, embedded systems, electromagnetic compatibility, and digital communications. So it's slightly broad. Yes, I will explain more in detail. They have skills in signal processing, digital electronics, analog electronics, whether it is low frequency or high frequency. They have courses for both. Electromagnetics and numerical methods, and digital communications. So it's very much related to our research, of course, because in our group we are quite a lot in being involved in this master degree. So just to give you maybe more insight, I'll just give you the overview of what they are following. The master degree in France is 2 years. This is the planning of the first year, and this is the planning of the second year. It is 2 years, but it's actually 3 semesters of courses and 1 semester of internship. Actually, they have also a second internship here during the end, at the end of the first year, but it is 2 months internship. This big internship at the end is 6 months. So if you are in the classical courses, you do those 2 internship wherever you want. If you are in the apprenticeship courses, you basically are full-time in your company during those 2 internships. So the first internship can be done in a company or in a research lab, such as the second one, actually. The students choose to go to companies or to a research lab, depending on their own interest. Usually what happens is that if they want to do PhD or work in academia, they will go to a research institute within a university hours or different universities. And if they want to work in companies, they will go naturally to companies. They could also do internship in companies and then do a PhD in a company associated with a university. That is also something we do. You can have students working on a research project in a company, and they are actually doing their PhD in the company, part-time in the company, part-time in the research institute, in the university. And that part-time actually can be very flexible. It can be 90% in the company, 10% in the university, or it can be the opposite, or it can be 50-50. It depends on the project. So I group here the courses by theme. So you see an orange. Oh, sorry. So one block is what we call 6 credits, ECTS. So that means 60 hours of teaching. And a half block like here, it's 30 hours of teaching approximately. So you see there is a bit of orange that is signal processing. There is a little bit of green, which is oriented object programming. There is quite some yellow, which is about analog electronics, quite some light gray, which is about analog electronics, but radio frequency, so mostly active devices, semiconductors and all. In light purple, this is about digital electronics, hardware mostly, and software a little bit also. In darker gray, this is about digital communications, but mostly soft. And in red, it is about electromagnetic and numerical methods. So you see, you have it's quite broad. but they have more background, I would say, toward hardware or electromagnetics. Although they do also have in embedded system with digital electronics, and usually depends on the students. But they have both these backgrounds, and you have also soft skills. So this is a professional integration. So we teach them, reteach them to do a nice resume. We prepare them for job interview. They have people from companies or from human resources in companies coming to the university to make talk, to talk about the social context and the economic context, where can they find job, etc. So it's to help them in that. And you see, although I know us French people, we are known for not talking English, we try our best, and we still have some English courses. So we just try. It's just we cannot. Must be in our genes, something. Yes. So when I give the course, I'm going to explain. You see, the students, they have a background. For my students from the master degree, they have a strong background, I would say, in antennas and propagation, and they have a lighter background on digital communications. So it was quite a challenge for me to make them up to speed in the digital communication skills. So I would show you at the end how I did do. I try to teach them some basics in digital communications, so that they have a certain level of prerequisites, and with a very limited number of hours. So now back to the courses. In this course, I emphasize on multiple antenna techniques, systems, and processing for the 5th generation of mobile communication. This, if you really want to understand this deeply, you need backgrounds in digital communications, signal processing, propagation channel modeling, antenna array theory, and transmission line theory to some extent for the architecture. So it's a very transdisciplinary course, and that makes it tricky because a lot of background are required. What I did is that, of course, I have to assume some basics are known, even though it's complicated because our students in the master degree come from our bachelor, but they can come from any bachelor, so they don't have all the same background. Fortunately, it's a second-year course, so they all have the first year. Normally, they all did the first year of our master degree, but sometimes it's not even compulsory. They could come from master degree abroad. They have their master degree and they do another master degree in just 1 year here. So anyway, I assume some basics were known, otherwise I gave them some materials to study. I reintroduced some basics during the course, and I gave them also some material to work the basics in autonomy. This I will show you at the end with MATLAB. It worked pretty well, I think. So I will just give you a brief introduction of the course so that you understand better the syllabus afterwards. I'm going to talk now about the 5th generation of mobile communication. With the commercial launch of the 5G in 2020, I would say that antenna engineers need more than ever to be aware of physical layer strategies that are currently being considered to reach expected performance. With techniques such as massive MIMO and millimeter wave communications, new challenges arise, and antenna engineers cannot afford anymore to be only experts in electromagnetics, but do also required skills regarding propagation channel, digital modulation, and coding aspects. So this is the transdisciplinary approach I was talking about. So the new communication schemes use advanced signal processing and coding techniques in order to exploit as much as possible the propagation channel to maximize some metrics such as the capacity. You want to basically increase the data rates. The antenna being a part of the channel, its properties influence the overall performance, and knowledge of physical layer features is therefore of utmost importance in the antenna specification and testing. So whether you work in signal processing or antennas, you need to know a bit of both the worlds to efficiently work in this new frame. So this course addresses important theoretical concepts in the field of antennas and propagation in the concepts of 5G. The first unit of the course introduces physical layer aspects, and the second unit tackles MIMO aspects, and I will explain them afterwards. And the third unit is about millimeter wave aspects. So before I actually explain more in detail each unit quickly, I want to talk about, I want to give you a brief introduction about the 5th generation of mobile communication for those who might not be aware of this field. And please feel free to once again interrupt me to ask any questions about this 5G. Sorry. So this is to give you a bit of context, this is the mobile data traffic per smartphone in gigabyte per month. So it's the use of people in different regions of the world. This is a source from Ericsson, who is a manufacturer of mobile network infrastructure. And you see this is the first bar is in 2018. This is North America. And the second one is 2024. So you see in everywhere in the world, there's a projection, there's anticipation that the consumption will increase a lot. So why is it so? Why do we consume more data in every part of the world? There is actually 3 main reasons. The first one is improved device capabilities. The smartphones are becoming much more powerful, so they can do more, so they do more, and they consume more data. The second one is almost everywhere in the world, we have more affordable data plans. The cost of the gigabyte is becomes less, and because more affordable to the larger number of people. So that means more people can use 4G, 3G, or other cell phone with internet, basically. And the third point is that the applications becomes more data intensive. Now applications require a lot of data to send and receive more data. So of course that consumes more gigabytes for the users. So this increase has been seen for a while now, and this is the trend. This is 2014, this is 2024, again it's a source from Ericsson, and this is the global mobile data traffic in exabytes per month, so the world data traffic. So you see a huge increase, and that it's expected to reach 131 exabytes by 2024. And you see that most of the traffic is handled by the existing infrastructure, the 2G, the 3G, the 4G. And from now on, 5G is being deployed. So 5G will absorb part of this traffic as well, and is required for that. So in this traffic, it's 90%, today it's 90% of the traffic is consumed by smartphones. Okay, no other device, not much other devices. And by 2024, it is expected that 95% of the traffic will be due to smartphones. So to absorb that, of course, 5G will help in handling global data traffic. But actually, 5G is not really meant for that. It's not the main purpose. 5G will also provide new features to handle new use cases, and 5G is not only for smartphones. It's to develop new markets actually. So for that, there are three use cases that are defined within 5G. One is a mode it's called enhanced mobile broadband. It's a mode that is supposed to support very high data rates, 10 of gigabit per second. So this is when you want to download like huge content in a second. A second use case, which is not possible right now. Another use case is to build ultra reliable low latency communication. So that is where when you want very reliable communication with low latency. but moderate data rate. This is again not very feasible right now with the infrastructure. And this is now not really for smartphone. This is more for industry to make anything linked to critical communications, such as the autonomous vehicles. I'll give a couple of examples after this. But this is not really for smartphones. And the other one is massive machine type communication. The idea here is to support a very large number of connection of devices for applications like Internet of Things. So here, once again, you don't want very high data rates, but you want a base station, a transmitter receiver, your infrastructure, you want it to be able to address thousands of nodes. And once again, it started coming in the 4G and the LTE, but it is now there much more in the 5G. So once again, this is not for smartphones. This is more for industrial or Internet of Things type applications. So you see, 5G is the main focus of 5G is not too much to improve the cell phone connection, which was already very good with the 4G. It's more to provide a seamless wireless network to any type of applications, especially toward industry. For example, in the ultra-reliable communication and very low latency will be used, is expected to be used a lot in vehicles, either in the factory, so in any factory actually. An example will be when you have robots that are making that are assembling some piece. They go very fast, and when there is a human coming nearby, the robot has to stop instantly. So right now this is done thanks to cable communication, wired communications, and that is what was not possible with wireless communications because the latency was too large. But now with this new mod, Ultra URLLC, this is supposed to be feasible. So you have very low latency communications. Same thing, it's for autonomous driving. If you want your car to be autonomous, you need it to communicate a lot with other cars, or a lot with roadside units, so with the infrastructure to anticipate any slow down or any accident or anything. So you need a lot of communication that need to be robust and very low latency. So to achieve those new modes, 5G rely on new improved technological improvement, and in this course I usually give them a few ideas at the physical layer. I don't explain the upper layer. It's not it's beyond my scope. So like there is an additional spectrum, there is some techniques such as carrier aggregation for those who know, there is a huge flexibility in the frame, the numerology, and there is massive MIMO and millimeter wave technology that are core of this course. But usually I give them a brief overview of all those techniques, because at least the students, they need to be aware of that, even not expert, they need to be aware of. So the 5G comes after 4 previous generation of mobile communication, and usually it's always the same thing. You have one generation starting something, and it's only the next generation that makes that work very well. So the mobile communication started with the first G, but it was only with the second G that it was working well. 3G start the mobile data, the internet, but it's only with 4G that it was seamless. I mean, the connection was fast enough to use it robustly. So 5G will start a lot of new things, but it will probably be only in the 6G. Some research, and also in the research we talk already about 6G, so it will probably be only in 6G that we will actually reach this kind of very stringent requirement in terms of latency or data rate. And 5G have started in some countries, very few countries in 2019, and some others now in 2020. So the infrastructures right now is very light. It's just the beginning, and it's more about updated 4G than a real 5G. So how a 5G is different from 4G. So 4G, also known as long-term evolution, focus was to enhance 3G's data rate. Whereas 5G, as I told you, the goal is much broader. It aims to interconnect people, but also and mostly to interconnect and control machines, objects, and devices. So 5G will exhibit more features than 4G, and you have a lot of improvement, but the goal is to use the spectrum more efficiently, higher data rate, but not the main goal, more capacity, this is an important goal, lower latency in some modes, and more cost effective. Okay. That's also another goal. So the standard has been released, so it's the consortium is the 3GPP. The 5G is the 3GPP release 15, and it is known by the public name will be 5G phase 1. This is this release. So a release is a set of specifications. This is this release that is being implemented right now. And the other release has been finalized recently, and others are ongoing. And the phase 2 will start in a few years only. So in 5G, it's important to know that there is 2 different frequency bands that are considered. Some are known as FR1, others as FR2. FR1 consider the frequency band below, typically we say below 6 gigahertz. So then it depends on the country, but most of the country have a band around 3.5 gigahertz. And then you have these FR2 bands that are much higher in frequency. We call that millimeter wave band. These millimeter waves band are also considered in different countries, but they are not being deployed as of now. The 5G you're hearing about is below, it's at 3.5 gigahertz. The millimeter wave will start after a few years. So you have a lot of bands for 5G, and 5G will also make use of the previous 4G bands, the LTE. We call that reforming. So all the previous GSM bands can be updated with 5G capabilities, at least some of them. So you see, so it depends once again on the country you live in, but it can be anywhere at 7 megahertz, 700 megahertz, 2 gigahertz, 3 gigahertz, 28 gigahertz. And the frequency actually influences the attenuation of the wave. When the base station transmits a wave, if it's in low frequency or high frequency, it's very much different. And this is the basics of why there are multiple antenna techniques, actually. So don't want to get too technical, but just when you have a base station and a cell phone, a mobile user that is at some distance away from the base station, you can actually calculate easily the attenuation of the wave between the base station and the user with some formula for a simple case here. So you see that it depends, this is the light velocity, r is the distance, so you have a constant term that depends on the distance, and you have another term that depends on the frequency. So the higher the frequency, this is minus, so the lower the path gain. So as the frequency increases, the wave attenuation increases as well, and the user will receive less power, so it will be more challenging to communicate, and the coverage of the base station will be more limited as well. To give you an idea, at 700 megahertz in this case, you have an attenuation of about 70 dB. If you are at 28 gigahertz, you have an attenuation of 100 dB. So you have a 30 dB difference, which is huge, and that will ultimately influence the cell coverage. So at 700 megahertz, you have a low attenuation, so you can have large cells, you have a good coverage, and you can use those for rural area or to address low data rate application. At 3.5 gigahertz, the 5G band that is being deployed right now, the cell are smaller, so it's more likely to be in dense urban environments where you can put a lot of base station a little bit everywhere, and you need high data rate because there is a lot of users. And the millimeter wave, as of now, it's not clear, but it will be most likely for hotspots only. So, for instance, a train station where you have hundreds of people packed in the same room, you need a huge capacity. There is a lot of connected devices, so you can add one hotspot in millimeter wave to not overload the whole network, for instance. And in those two frequency bands, you are actually making use in the 5G of multiple antenna based techniques. And this is why this course is about these techniques. Previously, a base station was a single antenna, not necessarily a single antenna, but a single beam, a large beam. So the base station will radiate everywhere, and any user within the coverage could receive the signal, but you need to share the resources between users. With multiple antenna techniques, you can actually, this is a multiple antenna system, you can create multi-beams, so you can focus the power towards some specific users. So you can improve the quality of the channel, and more importantly, you can reuse the same resource. So if I am communicating with user 2 at a certain frequency, I can actually use the same frequency to communicate with user 1, and each beam can carry different data. So you are more efficient, you use better the spectrum. And this course is all about that, how to process that. So now the syllabus of the course in more detail. Once again, if you want to interrupt me, please feel free. So it's divided into 3 units. The first one is a general introduction to 5G. So I talk about what I just talked right now, and I give that is how 5G is different from 4G, what are the main innovation of 5G at the physical layer that may influence the work of an engineer in the fields of antennas and propagation. And I make use of this unit also to review the basic concepts that I need to review. So that depends on the students I have in front of me. For instance, in our master degree, I need to reintroduce some basics in digital communications because they are more oriented towards antennas and propagation. So I will review modulation schemes, FDM, quickly multiple access techniques, or at least the architecture of a basic transmitter and receiver, and all the modulation like QPSK, 16 QAM, etc. So this I reintroduce in course, but quite quickly. So I will show you at the end. I have done some MATLAB live script for them, and they can actually implement all the basics so that I'm sure they master the basics. So the second unit is the core of the course. Is about MIMO technology. So I will detail a little bit each point. Antenna array theory, channel propagation, diversity, capacity, multiple antenna, MIMO processing. So it's quite broad. It's a bit challenging actually for students. So the survey antenna array theory, it's a prerequisite. So for my students in this master degree, they didn't need that, but it really depends on the courses they have done before. So the basic idea for them is to understand when you have, instead of having one antenna, this is a dipole antenna, instead of having one antenna, when you put 2 antennas into an array, the field radiated by each antenna will add up in some directions and will not in other directions. So you have interference between the waves radiated by each antenna. You have constructive interference, you have destructive interference, and you have an array factor, the radiation pattern of the array. And if you use a lot of antennas, you can actually create narrow beams, and you achieve a gain in that particular direction because you have focused the power. So that comes from antenna theory, antenna array theory. And I think it's necessary to know a little bit of that to understand the array gain in the processing later on. So I make sure the students know that, or I give them some materials. I give them basically a PowerPoint with the material for them to study that I can share also. Then I need to be sure that they have knowledge in channel propagation, which is hardly the case. It depends on, but in our master, they have not done any channel modeling so far, maybe very basic one. So in this course, I take some time to talk about the channel propagation. So as you may know, when you have a transmitter and a receiver in a urban environment, the wave is not just a line of sight. And even in some case, there is no line of sight because between the transmitter and the receiver, you have reflection on the building. You have, sorry, it's in French here. You have diffraction on the house. So the receiver will receive different replica of the same signal, and sometimes they will add up constructively, sometimes they will not. So the receive power will fluctuate a lot when the receiver will move a little bit, just a little bit. So we call that small-scale fading. This is an example. You have the receive power. You see that is very low, very high, depending on the location of the receiver. And you have characteristic about this channel. You have, usually you characterize it with statistical laws. So you have a number of criteria that describe the propagation statistically. And it's important for students to have a little bit of knowledge of that. So again, depending on what they have followed by, what courses they have followed before, I introduce quite some stuff here. Then I come to the core of the course. So I explain the concept of spatial and antenna pattern diversity and channel capacity for multiple antenna systems. So I'm not going to give the course now, but just the idea is when you have reflections of the waves within the environment, the one antenna of the receiver will receive two waves, for instance, path 1 and path 2, and the second antenna will receive the same waves, but with different phase shifts. Hence, normally, the signal received by antenna 1 and antenna 2 of a single receiver will be non-correlated. It will be different replica of the same signals with different statistics. And thanks to that, you can do processing to improve the channel capacity. And you can calculate the channel capacity. So I introduced those concepts, of course, more lengthy, more in details. And I explained them that the channel capacity, which is basically the maximum data rates you can, with which you can communicate in a certain environment with no error. I explained them that the channel capacity depends on the channel, the environments, whether there are buildings or not, reflections or not. And I also told them that it depends on the antenna as well. The antenna behavior is part of the channel. So I introduced some advanced concept of diversity and within antenna. So you have the well-known polarization diversity, but it goes further than that. So I explained them that the antenna properties are very important and that you can actually estimate the performance of an antenna system for MIMO in measurements or in simulations, but you have to take both into account. I'll just give you an example. I think this is a very important point. Recently, I have given a workshop, a training for engineers at Renault. So Renault is a French car company. And they were the specialists. They were engineers where they were actually doing the antenna measurements for their cars in an echoic chamber. So they, now the cars, they are more and more connected. So it were their service, their department, who were putting the antenna and all the transmitter receiver in the car, and they were doing some tests, and they were experimenting that. And they come because some other service told them, other department at Renault, they told them that 5G is coming. Now it's about MIMO, and you need to put multiple antenna systems in the car. They say, okay, we will put multiple antenna systems, but they didn't know why they had to put more antennas. So they didn't know whether they could put all the antenna in the same box in the cars, or they have to scatter the antennas all around the cars. So basically, they didn't know how to measure, to assess the performance of their antenna systems in a MIMO context, in a multiple antenna. MIMO stands for multiple inputs, multiple outputs. It's when you use multiple antenna to communicate. So this is important because you can put as many antennas as you want. It's not necessarily going to improve your communication if you don't know how those antennas are used by the signal processing. So once I explained that antenna is a part of the channel and it's very important to provide diversity, for instance, I introduced some signal processing, so MIMO processing. So all the precoding, decoding that make use of multiple antenna systems. So that use channel diversity, and we discussed the performance of those algorithms with respect to channel and antenna properties. So this is example where you have two antennas at the transmitter, one at the receiver, and the precoding here is there. So you have a signal that you want to transmit, you apply the precoding vector, and here it can be a simple beamforming. So the precoding will just create a beam towards the user, the receiver, basically. And then with them, I show them some bit error rate versus simultaneous ratio performance. So it's I show them how the algorithm performs with different assumptions, different channels, different antennas, etc. And at the end, with the projects they have, they actually can reproduce those results. So we do simple, we don't go for fancy precoding. It's just simple precoding, but basics ones. And the idea is for them to understand what's happening physically. And I complete this unit with a more practical point of view with respect to 5G. So I have introduced so far some MIMO processing, and I explain them in 5G. The signal processing we have seen is not necessarily implemented the same way, because you have more practical aspects to take into account. So usually, when you take that into account, you cannot do optimal precoding most of the time. So first of all, why? Because you don't know the channel most of the time. It's very difficult to know the channel to decide your precoding. So you have reference signals, channel estimation is very tricky. It's based on pilots. So at the end of the day, you end up doing precoding that are code book based. So I'm not going into detail, but it's just a suboptimal precoding, which is usually efficient enough and much more practical to implement. Finally, the last unit is about millimeter wave antenna array. So I'll talk about link budget, analog digital architectures, hybrid arrays architecture, and precoding channel estimation, and at the end, analog beamformers, which is more something as a perspective, more research-oriented, I would say. Even this whole unit is slightly more research-oriented because millimeter wave arrays are not there in 5G yet. It's uncertain as of now, which solutions is going to be used. So the link budget, it's the same thing as I told earlier. I just emphasize it a bit more in detail, and I explain them that the higher the frequency, the higher the attenuation. So because of that, in millimeter wave, the attenuation is very large. Plus, the millimeter wave doesn't go through a human body, it doesn't go through a building. So it's very tricky. And to compensate for this large attenuation, you need a large array gain. That is, instead of using one antenna, the transmitter, you need to use 100 of them, 100. So when you use antenna array with maybe 1,000 elements, you have two architectures that are possible. One is fully digital architecture. This is the architecture that is used in the 3.5 gigahertz band for 5G, the massive MIMO we hear about. So this is a fully digital. That is, each antenna is connected to a single radio frequency chain connected to a single analog to digital converter or digital to analog converter. So basically, you can manipulate digitally each signal that is being sent by each antenna. So that works well in the sub-6 gigahertz band where you have maybe 64 elements. It's already quite complex radio access antenna, and it's power consuming, but it's powerful, so we use it. However, in millimeter wave, if you were to use thousands of antenna, hundreds of antenna, you cannot use such architecture. It's too large. Plus, there are other issues as well. So you might go back to the phased array, which is well known by antenna engineer, which is an analog array. That is, you have a single antenna, a single signal, a single ADC DAC, so analog conversion, digital conversion, single radio frequency chain, and then the signal is split over each antenna, and you have typically phase shifter to control the phase of the signal radiated by each antenna. Thanks to these phase shifter that are electronics components, analog components, you can create a beam and steer the beam. So it's good, but that beam can you can create only one beam with unique data. So it means that using the same frequency resource, you can address a single user only. You cannot address multiple users. So this is limited. So what companies and researchers are investigating right now, it is a hybrid antenna arrays where, so I give two different architecture, but the idea here is that you have a digital precoding, an analog recording, and the number of radio frequency chain is not only one, but is not so large. Okay, maybe 10, 20, and the number of antenna is large. So it's kind of a trade-off between the full digital architecture and the analog architecture. So I just introduced this system-wise. Then I explained them that with those hybrid architecture, it's very difficult to estimate the channel, if not impossible. So you rely more on codebook-based precoding, where you have the base station that creates a beam, sweep the entire angular space, and just find the best beams among a certain number of beams. The concept of grid of beams. Finally, I talk about analog beamformers that are the Butler matrix and the lens, which are more research oriented. So this is more for students who are who would like to do research in this field mostly. I never had time to actually teach that. So I teach that just during projects, but not in the entire class. It's a bit too much otherwise for the course. So that's about the course and the unit. And I would like to end the explanation of the course showing you how with the labs actually. So it's a course I have recently designed. So there is no practical labs as such right now. I'll just give the idea I have for the future, but we have labs that are on simulations only. We use MATLAB for that. And we use labs to make sure the students have the prerequisites in digital communications. as well as to implement whatever we have seen in the course. So some labs, I am with the students, and some labs, they are supposed to do that in autonomy at home. And I will show you how I did manage for them to work efficiently in autonomy. So the labs, there are 5 sessions, and only 2 of them I am with the students. The 3 others, they are in autonomy. They are supposed to do certain amount of work on their own. And last part of that is a project. So here, the codes they have developed in the first sessions, they are using that code to implement something on top of that, which is a multiple antenna processing we have seen during the course. And the students will group into 2 with a group of 2 students, and they try to implement a project. So, and then I follow the groups through. Right now, it's mostly online through Zoom or whatever. And at the end of the project, each group of 2 students will present the outcome of the project. So I'm not asking them to present in detail their codes, but I'm asking them to present as if they were engineers in a company. So I want to see the results. I want to see which parameters they have change, and which type of performance they can achieve, etc. So the live scripts. So it's, I don't know if you're aware of that. I discovered that actually recently. In MATLAB, you can do what we call live scripts. So you can add text, figures, equations along with the code. I will show you. So the idea is to perform a simple digital communication scheme and to add then complexity. We start with basics and we add realism, we add complexity after each and every session. So each and every session use the code of the previous session. So you achieve a code in session 1, you further improve the code in session 2, further improve in session 3, and by the session 5, they have a complete framework of digital communications. I'll show you that the first session is simply you generate bits, so data, binary data. You do mapping to create symbols like QPSK16QAM, and this is the transmitter. And then you just add noise to create your receive symbols. So it's very simple: bits, symbols, symbols, and back to bits. We estimate the symbols, we do the demapping, and we calculate the bit error rate. Then we add some complexity. We add some. We add the pulse shaping, basically, which is we create the bits and the symbols, and then we pulse shape the symbols in order to obtain some time domain waveform. I will show you just after. So now we have a basement signal that is the same. We transmit, we filter, we estimate the symbol, we demap, etc. So now we have something which is more realistic. And then on top of that, we add the channel model, we add pilots to estimate the channel, and so here you have a complete framework. And then we add, the students add multiple antenna processing. So whatever we have seen in course, they have to try to implement it or even go further. So instead of talking too much about that, I will share my screen with MATLAB so that you can actually see how it looks like. I don't know if you still see my screen. Do you see the MATLAB file? So right now you should see a MATLAB file. I mean, yeah, you should see.
Yeah.
Yes. Okay, great. So this is a live script. So for those who know MATLAB, usually the program is a .m file. Here it's a .mlx. So it's a live script within MATLAB, but any MATLAB can do that. So you see, I can put figures, text, a table of contents, everything, plus code. So it's very nicely presented. I mean, it's appealing to the eye, so it works well with students. So typically, I give them a main. that is fully written. What I'm showing you right now, I give exactly that to the students. So I present them. Maybe we can do this example together so that you can see. I ask them, this is a symbol space simulation. I give them the flow chart, and then I explain what the code is supposed to do. So at the transmitters, the bits to be transmitted are mapped to complex symbol. These symbols are directly transmitted to the receiver. The channel is not considered. And so the only perturbation the transmitted symbols undergo is the thermal noise produced by the receiver electronics. The noise is modeled by a complex additive white Gaussian noise, ensuring a given signal-to-noise ratio fixed as an input parameter. The receiver then receives the received noisy symbols and convert them back to bits. The bit error rate is eventually determined by comparing the transmitted and the received bits. So they know what to do. I mean, the global picture. Then I give them guidelines, and the guidelines, so I explain them, but usually they have to fill up some functions. So this is the main, and if you see, they have to fill up 3 functions that are called in the main. The function, for instance, will be, I don't know, mapping, for instance. Where is mapping? Yes. Yes, so this is a function. Again, in the function, I give some details to help them. And this is the function. You see, it takes 3 variables as an input and 1 variable as an output. And I really tell them what are the inputs, what are the outputs. And I also tell them this is a vector of such dimension. And I give them actually the length of the vector and whether it's a column vector or a row vector. It makes debugging much easier for me if they use all the same size for the variable. So I told them this variable should have this size, etc. Then, for instance, in this example, they had to do the mapping for a QPSK and a 16 QAM. So I show them the constellation, I show them the bits according to the symbols, and here is the code they have to fill up. So, and for 16 QAM, they have to fill up here. Once they have filled up that, they can just run the main here, the main code, and see whether it works. So you see, the main, as I told you, is fully written. We have the input parameters, we have the transmitter, the architecture, generation of the bits is done, and here I call the function they had to fill. Then I also configure already the figure so that they can see the constellation, and they can see here a noisy constellation, the receiver, and the bit error rate. So they see directly the results. And honestly, there is a course, but most of the important stuff, is already written here in the live script. So it's easy for them. They have only 1 document. The material, the theory they need is within the MATLAB script, and it's well guided. So they can do almost everything by themselves. So that's why it worked quite well in autonomy. I'll show you maybe more advanced code like toward the end. What is this? Signal level. Okay, this is the same thing except we had the filtering, so there is more function to fill up. But this is for the 3rd session, I think. But most of the function, like half of the function, were filled up during the 1st session. So you have parameters. It's the same thing. I put comments. You have this is the impulse response of the filter. They plot it, and everything I ask them to do it without the MATLAB function, without the toolbox. So they have to redo by themselves. For instance, to design this filter impulse response, they have to use their own function that they have to fill up. And I also code the MATLAB function so that they can compare whether both the filter response are identical or not. Then they see the waveform in time domain, the baseband spectrum, and the receive symbols, etc. And this live script is nicely done. I mean, you can, it's very easy to edit. And if you have a lot of equations to put in your codes, you can even see, for instance, this equation, it's actually a LaTeX code. So if you have LaTeX equations, you can just copy paste here your equations from your course. And the editing is quite beautiful. So you see, this is where the students have to fill up their codes. And yes, what the last one with the channel and pilots, everything, I give them the flow charts and I explain the pilots. Sometimes I explain stuff here that I didn't have time to explain in the course, but it works well as well because they read it and they have directly to implement it in MATLAB. And I believe that when you code some concepts, you better understand them, I mean, more deeply. So yes, so this is with this is this is the 5th session output. So you have a longer code, and this is the beta rate curve versus the SNR for different channels. And this is based on this framework. Then they will add some extra processing. They will add extra processing during the project. So if you're interested in that, I can share also all the scripts with you, no issue. So just to conclude, so this is the labs in MATLAB. So it just requires MATLAB, and for the measurements with the hardware, as I told you, I have not done it yet. But what I intend to do is the following: is whatever they have implemented in MATLAB, it doesn't use any toolbox. So all the codes they have implemented can be seamlessly implemented into software-defined radio. So research-wise, I'm using USRP from National Instrument or ETUS. Those are these blocks controlled by the PC by MATLAB. And you have a mode that is offline mode. That is, you have your MATLAB code that make a modulation, generate a waveform, and the waveform is being sent to those boxes, and those boxes will just act as a digital to analog converter and will transmit whatever waveform you have done to MATLAB to the antenna. And with that box, you will receive the signal, convert into digital, and directly store it into memory that is being transferred to the MATLAB. So you are basically, you don't have to code FPGA or do a lot of stuff to go from simulation to measurements. You create everything software with MATLAB, and you just put your signals into memory, and the device will recreate your signal. So it's very quick, very fast to go from simulations to measurements. It's very seamless. And I think it's good for students because they have work on the simulation on the code, and then at the end they can actually measure in reality, see that there is maybe stuff they didn't expect from the simulation, some synchronization problem, etc. But it is very feasible in a very limited time because you go from simulation to measurements very quickly. Yes, that's about it. I think I will stop right now, and thank you for listening. And if you have questions regarding the course or whatever I talk during this session, please free to ask. Thank you for listening. Yeah, it's over on my side.
Okay, sorry. thank you very much for your presentation. If there is any questions, please. Some people wanted to ask me. So let me just check. So first of all, your presentation is directly for our university, I can say, because even my department and my neighbor departments, they are working with MIMO.
Okay.
Even my department, they're working on antennas and antenna propagation.
Oh, okay.
It was similar to me, and even 5G technologies. We also teach this for our students.
Okay,
And,
great.
not so much for space technologies because it is first time.
Yes.
We really want to work with you if it's possible, not only in Spacecom but in further works in collaboration with you. It would be very great if it's possible, like student exchange, or I don't know, try to Horizon, or what will be next in Erasmus.
Sure, sure. Yes, of course. We can discuss any possibilities. I'll be glad to. Yes, yes.
Thank you. So about questions, I don't know. For now, there is no questions. Maybe I think you had one more lecture or not?
No,
No?
no. This is no. This is lecture I was supposed to give on 5G. Yes.
Okay. Okay. So thank you very much. And your colleague would be, I think, at 4 p.m.
Okay. Because it has changed. He was supposed to be at 12, but I'm not.
Sorry, no, sorry. It is by Tashkent time.
Okay. Sorry.
12, it will be 4. Yes, sorry.
Yeah, sorry. No, my bad. Yeah, of course.
Yeah. 12.
Okay. Okay, so yeah, I'll make available those slides. I will ask Dimitri to share them, the content as well. If you're interested in those live scripts,
of course.
Yes, I will share that with you. And well, we can keep in touch. So for further collaborations, as you mentioned, do not hesitate to contact me, or I will ask Dimitri maybe also.
So you are also involved in Spacecom, yes, as I understand.
Yes. So the talk of today was not on space. I have a few activities on space. So with Dimitri, I have followed students who we had a project here at Sorbonne about nano satellite, and I was helping them in the communication, so in the link budget aspects or in the antenna aspects. Otherwise, myself as a researcher, I have worked a bit on. So my experience in space is mostly on antenna design. So I work on some projects with Thales or the CNES, so the French Special Agency, on antenna design for satellite mostly. And also we have collaboration with the French. How to translate that? The French Space Observatory, which is a research institute in Paris that again belongs to many universities. It's a bit complicated. So I work with them in this terahertz imaging. So they have one team at least is doing observation of the space in the terahertz frequency. And the trend earlier they were receiving terahertz from a single directions, and now the trend is to go for multiple pixels observation. So you have to integrate a lot of receivers, terahertz receivers, in the same place, and you have to feed them with the local oscillator. So you have to deal with that. So you need more. Maybe more advanced engineering components. So they ask us to some help for for what we know, this electromagnetic design. So the ref, I think I've presented quickly. When you have a local oscillator at terahertz that needs to drive multiple mixers, you need to split the local oscillator, and at those frequency you cannot do it with guided lines as you will do in lower frequency. So it's actually a beam that you divide, and you need to control very well how you divide that beam. So we do reflectors for that, for instance. So yes, I would say my involvement in space is more about electromagnetic device or antenna design, passive design.
Okay, and I don't know how it's possible about your syllabuses.
Yes.
Is it possible to share with us, and we could adapt our
the course of the content?
Yes.
Yes, sure. I think I have already, maybe it has not. I think I have already given the 2 first units, because at that time the 3rd unit was not over. But I can definitely share everything. Yeah, there's no problem. Yes.
And not only syllabuses, but also 1 or 2 examples of how to give, presentations, how to give to the students. It would be very great.
What I can give, I can give my slides. I mean, there is no problem. I think I already gave the 2 first units. I can give you the whole thing. And to have example, I think the best way, because I will just copy paste the link, because there is, when I did this course in Bombay in India, they were recording. So if you want examples, I think in addition to the slides, you can check this link. I don't even have the video recording, so I have myself also to go to this link if I want to see it. I think, as I mentioned, you probably need to give an email to log in, but it's completely free. And maybe importantly, the name of the course was,
so it is open, yes?
Sorry? It's open access. Open. Yes, it is an open access. Okay. Unfortunately, there is only half the semester, because after the COVID raised. The laboratory examples, sure, I will, let me write down slides and the live script. All the live script I show you, I can share them. There's no problem. It's I think it's better to share.
Not only slides of today's, maybe also for the course,
the presentation of the course, yes, to the presentation, I will make them available too. Yes.
I think today's lecture was not the same with your courses.
Sure.
It is not the specific ones, as I explained you. That we have all this kind of courses already, and your experience will be very great for us. And here's another question: how can we adapt antennas for 5G to our geographical areas? What do you think?
Sorry, in here.
The current antennas, 4G and 3G, to the 5G with the adaptation to the geographical areas, especially for some area.
Yes, so while the basic difference in the antenna actually that are already on the market, manufacturers are already selling. So there is, of course, the frequency, because in 4G, the 3.5 gigahertz band was not there. So of course you need a radio access with that particular frequency, and mostly you will simply have more inputs, outputs to your antenna system, because there will be more antennas, so more small power amplifier. So it's just more antennas, basically. Yeah? And specifications are a little bit different as well in terms of out of band rejection and everything. So this is one point. The other thing is that the 4G base station will be some of them at least will be updated to 5G capabilities, but of course with limited capabilities, because the 4G base station won't be able to cover those new bands. They won't be able to do massive MIMO as well as 5G. But all the improvements that are soft in terms of modulation schemes, in terms of flexible numerology. Everything which is soft can be, of course, reconfigured in the 5G base station. I mean, some of them and not all the features, but you will have some kind of 5G compatible base station using current 4G base stations. Yes, yeah. And otherwise, research-wise, I think there is more room for the antenna in the millimeter wave area, because in the 3.5 gigahertz you already have commercial products. So, yes.
Okay, thank you. So, is there any questions? If no, just let me thank our professor. It was a great lecture.
Thank you.
Thank you very much. And I think it is already lunchtime.
Almost. It's 20 to 12. We usually eat in France 12, 1 o'clock.
Okay.
Yeah, still a bit of time.
Yeah. Thank you very much.
Yes. You're welcome. Thank you. Thank you for listening. And I'll contact Dimitri to see how to share all those files with you.
Okay. Okay. If he could share with my email, or even I can write it.
Yeah, if you write me down your email, it will be easier, actually. I have to prepare something because I think it's file will be a lot. Okay, now let me copy paste.
Just for information, could I put your slides in the website of our project?
Yes, of course. The slide of today, you mean? Yes.
Today's, yes, of course.
Sure. Spacecom. Yeah, no problem. Slides of presentation, live scripts, and slide of the course, and link to video. Yeah, it is noted, so I won't forget.
Thank you very much.
Okay. So I wish you all the best with the next presentations. Okay, and I hope to talk to you soon then about some collaborations.
Thank you. And you're welcome to Uzbekistan. You can.
Thank you.
Thank you very much.
If the borders will be open.
Yeah, I hope so. Yeah, I've been actually once for vacation in Uzbekistan.
Whoa.
Yes, it was very nice. Very enjoy it. Very beautiful.
Well, you're welcome also. Again.
Okay.
Thank you.
Bye, everyone. Bye.
So I'm closing, and after 20 minutes, I will open the new session. Thank you, everyone. Yoki o'chirmayman, mana shunda turaversammi ekan. Assalomu alaykum.
Turaversa hamma kirib chiqayotmaydi bo'lmasam.
Yaxshi bo'ldi lekin. Zo'r.
Bravo. Boshqa masalalarni ham ko'ramiz bunda. Kafedrani masalasini.
Ha.
Qani oling, bu jala qo'lingizni oling.
Nimalar deyapsizlar?
Uzr. Shuning uchun yopib ochganim yaxshiroqmi deyman-da.
YouTube.
Assalomu alaykum usta.